Welcome to the first video of our journey in the quantum theory of NMR. Many of you would be intimidated by the topic, and I can understand why. When we talk about classical physics, we can always refer to what Galileo would define as sensible experience. These are our direct connection with various phenomena. In this case, the purpose of physics is to give a mathematical explanation of something we know very well. There are also everyday quantum phenomena, but we are experiencing them in a more indirect way, making them more difficult to understand. It does not help the complexity of the math involved to explain them. And this is another important problem. The connection between phenomena and math is direct in classical physics and usually involves a simple level of abstraction. Instead, the quantum world needs multiple layers of abstraction. My purpose here is to help you going through these different levels and really understand what is happening during an NMR experiment. Any quantum journey starts from the Schrodinger equation. Hc equal Epc. It may look a simple equation, but its implications are massive. Let's start with psi. This letter indicates a function that describes our spin system. We do not need to go deeper than that. H is an operator. That means it's a mathematical operation, and that's why it's applied to our psi. But H is not a normal operator. It's called Hamiltonian, and it describes the energies involved in our system. There are various formulations of it. One example is A times H bar times time derivative, where I is the imaginary unit and H bar is the reduced Planck constant. So the left part of the Schrodinger equation is just applying the Hamiltonian to the description of our system. This is equal to psi, where E is just a number, specifically is the energy of psi. Even not knowing the detail of it, you will agree that it's handy to just multiply psi by its energy instead of performing the derivation. What is important is that not all the psi's solves this equation. These psi's are special, and to understand why, we must analyze an important quantum concept, the Heisenberg uncertainty principle. Many know it and will tell a lot of jokes about the impossibility to know at the same time position and speed. As for many mainstream concepts, this statement is wrong. First is not speed but momentum, but this is not the main issue. The real problem is that the principle is not about the values of these two, but about their uncertainty. Specifically, the uncertainty product cannot be below a certain level. We can measure position and momentum of a particle, and as all measures, they came with a delta, an uncertainty. Usually, we can reduce their value with better equipment, but this principle is limiting us. The more precise we are on one value, the bigger the uncertainty on the other becomes. There is another version of this theorem about energy and time. The idea is the same, but let's try to combine it with our equation. The psi's that solve it have a very well-defined energy level, and if the uncertainty over energy becomes closer to zero, the uncertainty of time tends to infinity. But what does it mean, an infinite time uncertainty? It means that if we find our system in a psi state, we have no clue for how long it has been in that state. or for how long it will remain there. Therefore, they are called stationary state. So the stationary state solves the Schrodinger equation, and the Schrodinger equation is solved by the stationary state. The two things are directly correlated. Before moving on, I must introduce the standard quantum notation for formulas. The Schrodinger equation is well known and I was able to describe it without issues, but can be difficult to understand the meaning of each single letter. The Dirac formalism has exactly this purpose. It is also called the bracket notation from the name of these two more characteristic symbols, and its name is fertile ground for puns, so be prepared. We will use the cat to identify function and a small hat for operators. Since E is a constant, it will remain as it is. Now, it seems more like a quantum equation, and you may also notice why some quantum formulas are so overwhelming. All these symbols are there to help us understand what we are talking about, but the price to pay are more crowded formulas. Any quantum system is defined by its Hamiltonian and its stationary state. And this is why the Schrodinger equation is so important. If we work with the Coulomb Hamiltonian, we can calculate its stationary state, that are the atomic orbitals. But we work with NMR, and the Zeeman Hamiltonian is easier, and we already know its stationary state. In case of 1/2 spin, they are just the up and down state, often called alpha and beta, each of them with its own energy. Please notice the Z as a suffix to highlight the use of the Zeeman Hamiltonian. So, if our spin system is made from just one particle, we can write any general C as linear combination of the state alpha and beta. In this way, we can apply an operator. We can just apply it to our stationary state to obtain the result. But wait a moment. What does it mean? If our particle can be only up or down, what's the meaning of psi? This is our first level of abstraction. The coefficients are related to the probability to find our particle in such stationary state. Specifically, the probability is the coefficient times its complex conjugate. Since we are using real number, we can just use the coefficient square. So a C alpha of 0.87 and a C beta of 0.5 means 75% probability to find our particle in the up state, a 25% probability to find it in the beta state. Remember, it's not the coefficient itself, but its square. Of course, the total probability must be 1. The particle must be in some state. So, this is the point. Quantum physics is not about predicting the behavior of a particle. We must get rid of this idea. We can only predict the probability that a certain particle is in one state or in the other. So everything is going to be described as a change in probability. You may think that it makes no sense, and you will be right. Also, Schrodinger had this opinion, and he made a mental experiment to demonstrate it. The Schrodinger cat. I will present a small variation applied to NMR. Let's take a big box where I put an NMR magnet with a single proton inside. This instrument is connected to a vial of poisonous gas. that it breaks if the instrument detects something. Together with this evil machine, we also put a cat, and we close the box. Our nucleus starts in the beta state. We know it will decay, but until that moment the NMR instrument will remain quiet. The vial sealed and the cat alive. When our proton decays to alpha state, the system will detect something. The gas will be released and the cat will die. Since the box is closed, we have no way to monitor the proton, so we will describe it as a linear combination of alpha and beta. So we are describing the proton as in both up and down state. That means that at the same time the NMR have and haven't detected something. The gas is contained and released, and the cat is both dead and alive. This is absurd, and that's also the point. The quantum realm is weird with behavior that have no equivalent in our macroscopic worlds, and are alien to our mind. Our journey continues in the next video. Thanks for your attention.